So now we're going to look at our velocity notes. So velocity is a lot like speed. So we can think about this kind of as just like speed. There's a couple of minor differences, but we'll get to that in a little bit. First up, the guiding question for this set of notes is how do you figure out how fast something is going? Okay, so the big idea here is the change in an object's position, aka its displacement. Remember that was our last set of notes, is that we have a position, which is where you are, and then the displacement is how far you've moved, basically. Remember, algebraically, that's a delta x. The delta means change in, final minus initial, x is for position. Uh, so we have its per unit time is defined as its average velocity. So mathematically, all that is delta x, your change in position, your displacement, divided by your change in time. How far you moved divided by how long that took you. That gives you your average velocity. Since delta x, your displacement, can be positive or negative, so can velocity. So that's what makes velocity different than speed, is that velocity has a direction. You can be moving in the positive direction, you can be moving in the negative direction, versus speed does not have that. So that's kind of one of the differences, right? Velocity can be positive or negative, speed cannot. So let's consider that we're looking at a graph here. Okay, so you should have already copied this into your journal. Consider a position versus time graph below. So we got our position, we got our time. This object is starting at 10, at initial position of 10 meters per second, and is moving at a constant velocity. I know that because it's a linear line, constant velocity in the positive direction, right? Because it's going right 10, 20, 30. So its position is increasing. Okay, so if we look at the slope of this graph, the slope would be the rise over the run. So our rise would be a change in position, right? Because that's what's plotted on my vertical axis is position. So I've gone from, in this case, 20 meters to 40 meters, right? So I've changed my position. So that's a delta x. And then my run is a delta t, a change in position, right? Because I've gone from 2 seconds to 6 seconds. So if I was to find my average velocity, what I'm really going to, right, delta x over delta t, hey, look, that's the same as it is up here. So to find, right, that means that the slope of this line is the velocity, how fast something is going. So the slope is, in this case, would be the final position, 40, minus the initial position, which is 20, over the final time, which is 6, minus the initial time, which is 2. It gives you 5 meters per second, which is the slope of this line and also how fast the object is going. So, right, for a linear graph, a linear graph is going to tell you that our object is moving at a constant speed, right? Remember, linear lines in math can be done as y is equal to mx plus b. That's just the general form for a linear graph. So if we look at this, right, y represents where the car is. So we're going to replace that with an x because remember we use x for horizontal position. Um, Sorry that this is out of order a little bit, but our y-intercept is going to become the initial position, and the slope is going to become the average velocity. So that's what's going on there. And the x is, right, we have time plotted on the x-axis. So that's how that's happened. So sorry that I kind of flipped things around, but again, position is what's on our y-axis, so hence the x. The y-intercept represents where the car starts, hence the x naught, because x represents position. The little naught here represents when time is equal to 0. And so that's what the x naught is, plus, and then remember the slope is the average velocity, and the time, and then right x-axis is the time. So now let's take a look at some example problems. So I'm going to flip over to a blank one of these. So here's our example problem. So let's take the equation from the last graph, meaning, right, meaning this graph right here, because its slope was 5 and the y-intercept was 10. So therefore, the equation for that line would be x is equal to 10, because that's the y-intercept where the car started, plus 5, which is the velocity times by t. That's the equation that represents the motion of that tumble buggy. So then Okay, so that's just writing the equation for the last graph. Let's take a look at an example problem now, a different one. Okay, so let's say this is our graph here. Find the average velocity for each time interval. And by each time interval, what it means is each distinct piece of the graph. So, right, we have three distinct pieces of the graph. We have this part from 0 to 2 seconds. We have a different part from 2 to 3 seconds, and then another part from 3 to 6 seconds. So find the average velocity, aka find the slope, right? So what it's asking is find the slope, right? So the slope of this first chunk is going, right, we're going to go down 1, 2, 3, 4. So down 4, so -4 over 2, which is just going to give you -2 meters per second. This one, the slope of this line is 0, right? It goes down or up 0 and over 1. So 0 divided by 1 is going to give you 0 meters per second. And this part is going to go, right, it goes up 1 over 1, 2, 3. So that's going to be up 1 over 3. So 1 divided by 3, rise over run, which is going to give you 1/3 or 0.3 meters per second. Okay, so these are our three velocities here: -2 meters per second, 0 meters per second, and positive 0.3 meters per second. So those are the average velocities for each time interval. So now plot a position or a velocity versus time graph. So between 0 and 2 seconds, our velocity is -2. So let's do this. We have -2 meters per second, -1, 0, +1, +2 meters per second. Okay, so from 0 to 2, right, that's down there. 0, just going to color it right in there so it's obvious that it's 0. And then 0.3. So 0.3 is going to be, this is 0.5, so 0.3 is going to be right in here. Somewhere in there. So we have these kind of like three chunks of horizontal lines, right? It's a horizontal line because it's going negative. The slope is -2 here, -2 here, -2 here, -2, -2, right? This whole time, the slope is -2 for this, right? Any time between 1 and 2 seconds, the slope is -2, meaning that you're going -2 meters per second all like this entire time. So therefore, when we make a velocity graph, we're going -2 this entire time. Then, right, the slope here is 0, meaning that you're not moving for this entire time interval from 2 to 3. And right between 3 seconds and 6 seconds, you're going +3 meters per second. So therefore, this graph is going to be +3.3 the entire time. So that would be making a position versus time, or a velocity versus time graph, and how you would go from making a position versus time graph to a velocity versus time. Okay, we're almost done. We got one more thing here. So the last thing we need to do is we just have some key facts that you need to get down here. So lastly, so there's a very important difference between speed and velocity, right? I said at the beginning of this video that we were going to talk about that. So speed is how fast an object is going. And technically, depending on what math class you are, this would be a scalar. You don't really need to know what that means, but it's simply just a number with no direction on it. Velocity is how fast you're going and in what direction. And generally that direction is denoted by a positive or a negative sign. So you're going in the positive direction or a negative direction. Remember back to when we talked about position, we usually think about things as being on a number line. So positive direction would be usually going to the right, negative direction would be going to the left. But it could be, right, direction can be also described as up, down, right, left. So, but how fast and in what direction, okay? Algebraically, when we go to find speed, you would look for the distance that the object traveled over the time, and for velocity, it's displacement over time. The difference here being, right, so if we were to look at let's go back to our graph, right? This graph here, the distance that the object traveled, right? It traveled 4 meters because it went from 5 to 1, so it's a distance of 4 meters, and then it traveled 1 meter back the other way. So that would be a total distance of 5 meters because 4 in one direction plus 1 in the other. Total thing took 6 seconds. So that's going to be 5, right? It's gone, like its speed would be 5 divided by 6 or 0.83 meters per second versus the velocity displacement, right? Remember, displacement is just final position minus initial position. So its final position is 2 because we ended at 2. Its initial position is 5 because it started at 5, and then divided by 6 because it took 6 seconds. So that would be -3 divided by 6. So its velocity would be -0.5 meters per second. So here's an example of where speed and velocity are different. And right, note the negative sign, which right tells you that the average velocity was in the negative direction, versus note that speed again does not have a direction, so it's just no negative sign there, even though ultimately you travel in the negative direction. So that's an end. That brings us to the end of the velocity notes. So thank you for watching.